Dear students, in this video lecture we will learn about degrees of freedom. We will also try to derive expression for degrees of freedom, and we will also try to solve some problems on degrees of freedom. Degrees of freedom is basically minimum number of independent input parameters required to define position of each and every link in the mechanism with respect to fixed link. Now we all know that every mechanism has a fixed link. Well, the kinematic chain is converted into a mechanism by fixing any given link. Let us say I am considering this 4-bar mechanism. Link AD is frame, which is link number 1, and it is fixed for us. AB is acting as a crank, and I am calling that as link number 2. BC is the coupler, I am calling this as link number 3, and CD is the follower, I am calling this as link number 4. So in this configuration, if we want to define position of link number 2, 3 and 4 with respect to link number 1, which is fixed, then I am in need of certain input parameters apart from the dimensions of the link. Let us say L1 is the length of the frame, L2 is the length of the crank, L3 is the length of the coupler, and L4 is the length of the follower. Now all these L1, L2, L3 and L4 are given to you, and if it is asked to you to determine position of crank, coupler and follower with respect to frame, then you will be in need of one input parameter, which is, let us say, this angle theta, to redraw this particular figure and to get position of each and every link with respect to link AD. So let us say position of point A and D is already known since it's a fixed link. With this given angle theta, I will determine position of point B. Then with B as center and BC as radius, I will be drawing one arc, and with D as center and DC as radius, I will be drawing one more arc, and their intersection will give me point C. So apart from L1, L2, L3 and L4, I am in need of theta to determine position of other links in the given mechanism with respect to fixed link. So this theta becomes independent input parameter. Now degrees of freedom is nothing but how many number of independent input parameters are required to define position of each and every link in the mechanism with respect to fixed link. That number is nothing but the degrees of freedom. Let us try to understand the concept with one more example. Now let us consider a single slider chain. Once again, link number 1 is fixed right over here. Link number 2 is obviously the crank, which is link O to A. Link number 3 is the coupler, which is AB, and link number 4 is basically the slider. Now in this configuration, if I wanted to determine position of all other links with respect to the fixed link, then I am in need of this angle once again. So by knowing position of O2 and this angle theta, it is possible for me to locate this point A, and then simply knowing distance AB, I can draw this particular arc, and it is easy for me to locate this particular point B. So apart from the length of the link, I am in need of this input parameter. Now number of such inputs parameter determines the degrees of freedom. So the minimum number of independent input parameters to define position of each and every link in the mechanism with respect to fixed link is nothing but the degrees of freedom. Now let us try to find out the degrees of freedom for this 5-bar mechanism. AE is link number 5, let us say. AB is link number 1, BC is link number 2, CD is link number 3, and ED is link number 4. L1, L2, L3, L4 and L5 are the length, and L5 AE is the fixed link of the mechanism. Now once again, to determine the position, how many number of independent input parameters are required? Let us try to find it out. Now since I know position of point A, initially to determine point B, position of point B, I'll be in need of this particular angle. Let me call this angle as, let us say, theta 1. So by knowing L1 and theta 1, it is easy for me to locate point B. Then to locate point C, with B as center and BC as a radius, I will be drawing this arc. However, I will not be reaching to point C. So now I'll take reference of point E right over here, and I'll try to locate point D. Now to locate point D, apart from L4, I am in need of one more angle right over here. Now let me call this particular angle as theta 2. So by knowing L4 and theta 2, it is easy for me to locate point D. Once I get point D with D at center and DC as radius, I will be drawing one more arc, and then the intersection of both arc will give me point C. So with this, it is possible for me to complete this particular diagram. Now if you notice, in this particular configuration, two independent input parameters are required. The first one is this angle theta 1, and the second one is this angle theta 2. So in this configuration, the minimum number of input parameters required to define position of each and every link in the mechanism with respect to fixed link are 2. So the degrees of freedom for this mechanism is 2. Well, the degree of freedom is typically denoted by letter small n. Now with this discussion, let us try to generalize and try to obtain the degrees of freedom for let us try to obtain the expression for degrees of freedom. Now what you see on your screen is basically a rectangular coordinate system. Let me call this as figure number 1, figure number 2, figure number 3 and figure number 4. Now in figure number 1, in a rectangular coordinate system, I have considered two links. Let me call this as link number 1, which is a fixed link, and here is link number 2. Now in order to define position of this link number 2 with respect to fixed link number 1, how many number of independent input parameters are required? Let's check it out. So here are those independent input parameters. In order to define position of this point, I am in need of its coordinates, which is x and y. Once I get position of this point, then I'll be in need of one more input parameter, which is theta, to finalize the position of link number 2 with respect to link number 1. So we can conclude, in a rectangular coordinate system, every link in space has 3 degrees of freedom. Every link in a space has 3 degrees of freedom. Now what we'll do, we will try to concentrate on figure number 2. Once again, the same rectangular coordinate system, same link number 1, which is lying along the x-axis and fixed. And now what we'll do, we will try to form a turning pair between link number 2 and link number 1 at this particular point. Now after forming a turning pair, how many number of input parameters are now required to define position of link number 2 with respect to link number 1? You will notice now you are not in need of x coordinate and y coordinate, you are only in need of this particular angle theta to determine position of link number 2 with respect to link number 1. Now the pair formed at this particular point is basically a lower pair. We know that turning pair falls into the category of lower pair. So once again I can generalize, at every lower pair formed 2 degrees of freedom will be lost. Earlier this was having 3 degrees of freedom. Now after forming a lower pair, out of 3, 2 degrees of freedoms are lost and only 1 degree of freedom is left behind. So I have said that at every lower pair form 2 degrees of freedom will be lost. Now let us concentrate on figure number 3. Once again the same rectangular coordinate system, same link number 1 which is lying along x-axis and it is fixed, and now I'll consider a disk. Now according to the earlier discussion, once again this disk will have 3 degrees of freedom. It can move in this direction, it can move in this direction, and it can even turn in clockwise or anti-clockwise direction. So as I've said already, every link in a space will have 3 degrees of freedom. Now let us say this link forms a rolling pair with fixed link number 1. So please refer to figure number 4 now. This link has now formed a higher pair, because we know the pair formed right over here is a rolling pair, and that basically falls into the category of higher pair. So now this disk has formed a higher pair with a fixed link, and now how many degrees of freedom are lost? Let's check it out. Now in this configuration, this vertical movement of the link is now restricted. Now it can only move in this direction, horizontal direction, and even it can turn in clockwise or anti-clockwise direction. So in this particular configuration, after forming a higher pair, at the given higher pair, 1 degree of freedom is lost. Like I said earlier, in this configuration this disk was having 3 degrees of freedom. Now out of those 3 degrees of freedom, 1 degree of freedom is lost and 2 degrees of freedoms are still remaining. So from this discussion we understood that every link in a space will have 3 degrees of freedom. Whenever that link forms a turning pair, then 2 degrees of freedom will be lost, or when it forms a lower pair, 2 degrees of freedom will be lost, and when a link in a space forms a higher pair with any other link, 1 degree of freedom will be lost. So let us try to calculate the total degrees of freedom with this example. Once again the same 4 bar mechanism is considered. Frame is basically the fixed link, and apart from frame there are 3 more links. There is crank, there is coupler, and there is follower. Now each of them will have 3 degrees of freedom. So crank will be having 3 degrees of freedom, this coupler will be having 3 degrees of freedom, and this follower will be having 3 degrees of freedom. So all in all, this configuration will have 3 plus 3 plus 3, total 9 degrees of freedom will be there. Now what we'll do, let us allow this crank to form a turning pair with the frame. So like I said earlier, we were having 9 degrees of freedom, and now this crank has formed a turning pair with the frame at this particular point. So from 9 you have lost 2 degrees of freedom, because we have understood that at every lower pair form 2 degrees of freedom will be lost. So this will be having 1 degree of freedom now, this is still having 3 degrees of freedom, and this is still having 3 degrees of freedom. So now the total degrees of freedoms are obviously 3 plus 3 plus 1, which is 7. So like I said earlier, all 3 of them were having 3 degrees of freedom each, so total degrees of freedom were 9, and after forming a turning pair 2 degrees of freedoms are lost, so now you are having 7 degrees of freedom. Now similarly, let us move on and let us form a turning pair between crank and coupler. So now we were having 7 degrees of freedom, and now this crank and coupler have formed a turning pair at this particular point. So once again you will notice that at every turning pair formed 2 degrees of freedom will be lost, right? So from this 7 I'll subtract 2, and now I'll be having 5 degrees of freedom. Now 5 degrees of freedom, this one is right over here, 1 for this coupler and 3 remaining obviously for the follower. Now once again I'll form a turning pair between coupler and the follower. So earlier we were having 5 degrees of freedom, and now the coupler has formed a turning pair with the follower, so 2 more degrees of freedom will be lost, and there will be only 3 degrees of freedom will be remaining. So 1 for crank, 1 for coupler and 1 for the follower. So total 3 degrees of freedom are remaining, and at the end let us allow the follower to form a turning pair with the frame. So earlier configuration 3 degrees of freedom were there, and after forming a turning pair between the follower and the frame 2 more degrees of freedom will be lost, and 1 degree of freedom is left, which is the degree of freedom for this particular mechanism. Well, in our initial discussion, if you remember, we already had a discussion that apart from the dimensions, this independent input parameter is required to define position of crank, coupler and follower with respect to frame. So that gives us to degree of freedom equal to 1. And with this discussion even we have understood that how to obtain the degrees of freedom. Now let us try to generalize the things. So in a given mechanism, if let us say we have L number of links, then how many number of moving links will be there in that mechanism? We know in a kinematic chain we always try to fix one link. So if it is a 4-bar chain, then link 1 will be fixed and 3 will be moving links. So in a given mechanism, if you have L number of links, then number of moving links will be L minus 1. Now each of them will be having 3 degrees of freedom. So the total degrees of freedom will be 3 into L minus 1. Now let us say we form we form J number of lower pairs, and we know that at every lower pair form 2 degrees of freedom will be lost. So once we form J number of lower pairs, 2 into J number of degrees of freedom will be lost. So now the remaining degrees of freedom will be n is equal to 3 into L minus 1 minus 2J. And let us say we also form H number of higher pairs. So as we know that at every higher pair formed 1 degree of freedom will be lost. So now the total degrees of freedom will be 3 into L minus 1 minus 2J minus H. Now this expression of degrees of freedom is called as Kuchbrach criteria. Now this expression is typically used to obtain the degrees of freedom for different mechanisms. So let us try to solve some problems on degrees of freedom. Now once you get the number of degrees of freedom, you will have to interpret that particular number. So if n comes out to be equal to 1, then your interpretation must be a mechanism is driven by a single input motion. If value of degrees of freedom comes greater than equal to 2, then your interpretation must be more than one input motions are required to produce a constrained motion. If n is equal to 0, then no relative motion is possible between the members, thus it forms a structure. That must be the interpretation. And if n is less than 0, means minus 1, minus 2, something like that, then redundant constraints are added and hence it becomes a structure. Now this redundant stands for unnecessary, the constraint which are not required. So unnecessary constraints are added in the chain and thus it becomes a superstructure. So these interpretations should be written right at the end of every problem on degrees of freedom.